Okay, let's try this again. Use the change of variable x equals 1/2 u plus v. So the same change of variable y equals -1/2 u minus v to evaluate the double integral of 4 times x plus y times e to the x minus y dA over the triangle bounded by the vertices -1 to 1, -1, 1, 1, 1, and 0, 0. Okay, so what's the problem with this kind of triangle? If we look at it from a visual perspective, we have -1, 1, 1, 1, and 0, 0. What that is a triangle that doesn't have a clear horizontal or vertical. So this conversion for us, again, we know because it's the same conversion that x minus y equals u and x plus y equals v. And since it's the same conversion, our Jacobian is still 1/2 from the same problem from the last video. So what does this do to the vertices of our triangle? -1, 1, -1 plus 1, or -1 minus 1 is -2, -1 plus 1 is 0, 1, 1, 1 minus 1, 0, 1 plus 1, 2, and 0, 0, still 0, 0. So what did it do to our triangle? It changed our triangle from this awkward downward facing one to a nice convenient one. It kind of rotated it. What does that do? Well, it lets us have clear bounds either in the x or y direction. In this case, the u or v direction. So even though our integral is going to depend on one or the other, it's much easier to deal with this than to deal with that one. So when I convert, and of course, this integral is ugly, it should be nicer now. So we've got 4. X plus y we know is v. X minus y, so this is now e to the u, times the Jacobian of 1/2. So 4 times 1/2 is 2, so we bring it out. So it's now v times e to the u. So let's talk about u and v. We know u goes from -2 to 0. We know v goes from 0 to 2. How do those two relate? If we're talking about the triangle, v is always less than or equal to u plus 2. Looking at this line here as we go, this is the line. This would be the line y equals x plus 2, but y in this case is v equals u plus 2 by comparison because this is a uv graph. So that means v goes from, instead of 0 to 2, it goes from 0 to u plus 2, and if we do v first, that's fine. So we have 2 and an integral from -2 to 0 for u, and then v goes from 0 to u, or 0 to v, u plus 2, blah. So this is v times e to the u, and now we have to do v first in order for this to work. What happens when you integrate with respect to v? Becomes 1/2 of v squared e to the u, evaluated from 0 to u plus 2. 2 times 1/2 is just 1. I know I always write diagonal on this, I don't know why. -2 to 0, this is now v squared e to the u, evaluated from 0 to u plus 2, and we still have a du in here. It becomes u plus 2 squared. So this will become u squared plus 4u plus 4, all times e to the u, du. In order to integrate this, we are going to have to use, let's separate to pieces. I'm going to go from -2 to 0 of u squared e to the u plus 4u e to the u plus 4e to the u. The integral of this one should be integration by parts. So we'll do the tabular method. u squared e to the u, 2u, 2, 0, e to the u, e to the u. So this one should be u squared e to the u minus 2u e to the u plus 2 e to the u. This one is 4u, then 4 e to the u, e to the u. So plus 4u e to the u minus 4e to the u. The integral of 4e to the u is just plus 4e to the u. Evaluated from -2 to 0. Let's simplify. We've got a u squared e to the u. Minus 2u plus 4u is plus 2u e to the u. -2, or plus 2e to the u minus 4e to the u plus 4 should just be plus 2e to the u, evaluated from -2 to 0. Now when I plug in 0, I just should get 2. Because the 0 is going to cancel out here. When I plug in -2, I'm going to get 4 over e squared. Here I'm going to get -4 over e squared. And here I'm going to get plus 2 over e squared. Those two are going to cancel, so this should just be 2 minus 2 over e squared. If you want a common denominator for that, it would be 2e squared minus 2 over e squared. It's the value of that integral. And that is all for 14.8.